In that case, let's move on to the next talk, Enhancing Network Diagnosis with Reflection in Prolog by Anduo Wang.
Hi, Anduo Wang here with Temple. In this presentation, I will talk about enhancing network diagnosis with reflection in Prolog. So why network diagnosis? On the surface, networking has been a tremendous success. Just look at this internet today, this global infrastructure. Compare it with the original ARPANET. But if we look closer, inside, network management is a completely different story. Network systems are increasingly complicated. The traditional network diagnostic tools based on trial and error, pin and trace route, became a black art that's no longer adequate. So in the past 10 years, to address this limitation, we are seeing more and more use of static analysis for diagnosis of networks. And here's a few publications appearing in major networking venues. And here's more events in both industry and academia. So one notable thing we observe here is the majority of these work are on verifying data centers. These are lightning-fast network verification tools for hyperscale data centers developed by big companies like Microsoft and Google, etc. A key enabler here is the use of software-defined networking, SDN, that views a network as a network-wide program. This program perspective transforms network diagnosis into a static analysis task. What is often neglected in this data center diagnosis, I would argue, is a unique characteristic of data centers. Data centers, unlike any other networks, they are clean slate, homogeneous, well-planned, and over-provisioned. They play a key role. This becomes even more clear if we make a parallel between formal diagnosis in data center and program analysis in compilation. In both compilation and data centers, we are facing problems that are well understood and oftentimes prefixed, where the performance is a major concern. For example, compilation, we deal with optimization. And in data center, almost all the tools we've seen in the previous slide, they're about reachability verification. So not surprisingly, despite their difference, both solutions oftentimes take the form of highly optimized heuristics over carefully crafted data structures. But in the wild, the majority of the networks, they are not like data centers. They are not clean slate. In the wild, no two networks are the same. And networks are always evolving with unanticipated changes. Just like in the generic programming environment, no two programmers are the same, and we need to support the entire life cycle of software development. In other words, the problems in programming environment and in the majority of networks we need to deal with in the wild, we are facing problems that are more diverse compared to data centers. We need to support the entire life cycle of the system. And here, in addition to performance, usability also matters. We need simple, flexible, and extensible support. And we argue that the solutions that originally developed in general programming environment, such as profiling, monitoring, tracing, or the more sophisticated algorithmic debugging, abstract interpretation, program slicing, etc., these tools, they will have great potential for networking as well. And in this talk, I want to present some initial encouraging result in developing explanation and test generation tool for networking by using Prolog. The idea here is that Prolog provides a very natural way to write meta interpreters that offer an injection point of these new solutions. In particular, I want to show you how Prolog can help us debug internet routing. How Prolog's unique programming style that combines declarative logic and imperative control offers a natural spec for the dynamic and non-convergent behavior of complicated internet routing behavior, and how Prolog's metaprogramming facility allows us to quickly write meta-interpreters that can explain the internet routing behavior. But first, let me provide some necessary background on internet routing. Internet routing is about computing paths between any pair of source and destination on the global internet, oftentimes across multiple independent operated networks, the so-called autonomous systems or ASs. To automatically do this job, internet routing uses BGP, Border Gateway Protocol, as a distributed algorithm. So BGP computes, in networking jargon, inter-AS paths, a shortest path that modulated modular traffic policies set by individual ASs along the way. Traffic policies are necessary for ASs to express their local, oftentimes economic concerns. Just like most things happening in computer networks, BGP is not a protocol that's well planned. It's incremental patchwork. It involves a sequence of attributes that are orderly compared in path selection. It also involves several scaling methods. What's relevant in our talk here are two attributes and one scaling method. The first attribute is next hop. That allows us to select the closest exit point. The idea is every AS, consider the center AS example, every AS would like to get rid of traffic as soon as possible. So we always pick the shortest internal path, in this case highlighted by red path. The next attribute relevant to our debugging here is MAD, multi-exit discriminator. MAD is the attribute set by an AS to express its preference how traffic enter it. For example, ASX can use 10 and 100 to be associated with CA and CB link here, expressing that it favors CA over CB to receive traffic. And finally, we need to understand reflection. Without reflection, BGP requires a full match between any pair of BGP routers so they have consistent view. But with reflection, the idea is some routers now will serve as reflectors that reflects routes on behalf of other nodes. Clearly, reflection is a very useful scaling technique to remove that full match requirement. So at this stage, we've discussed three important aspects of BGP. Each looks very useful, but putting them together, we will see unexpected, indeed harmful result, oscillation, as highlighted in this example, first introduced in RFC 3345. In this example here, we are interested in computing paths to the destination in the bottom. The interesting part here is AS1. AS1 has two reflectors, RA and RD, that are connected with each other, and they will reflect information on behalf of each other, as well as RB, RC, RE. So initially, RA and RD each gather information from their direct neighbors RB, RC, and RE. RA will have two options, as we can see on the RA column here. Out of the two options, RA will pick the red path because it has a shorter next hop cost. On the other hand, RD will simply pick the blue path. That's its only option. Now in the next iteration, RA and RD, they will reflect their information to each other. After RD receives information from RA, which is a pass, RD now have two options, and out of the two options, RD will stick with its old blue choice because it has a better MED. On the other hand, after RA receives this new blue path from RD, RA will change its selection. What's interesting here is the newly arrived blue path will beat the previous selected RA-RC path. However, it wouldn't make the blue path itself the best path for RA. Instead, it will cause RA to reselect a previously discarded red path. Next, as RA and RD each has updated their routing path, they will reflect and notify each other. So in the next iteration, after RD receives this new path from RA, it will update its current best path accordingly, and that will actually trigger RD to change its selection, as highlighted in the figure here. Similarly, after receiving the update from RD, RA will change its selection again. And now we can see a repeating pattern. RA is going back to its oldest state, and similarly, RD is going back to its previous state. And such oscillation can keep forever. So through this simple example, we see that seemingly innocent BGP configuration can lead to undesirable oscillation behavior. What is worse? It's tedious to detect manually, and to our best knowledge, despite of the significant progress in data center verification, none of the existing tools we are aware of can debug, can explain such oscillation. And in the rest of the talk, I want to show you how Prolog can help us to debug it automatically. Our Prolog implementation was tested in XSB and freely available on the GitHub repository here. But in this table, I want to show you how compact and concise our code is. You can see that the BGP protocol, of course, we didn't implement the complete protocol. We only implement the aspects relevant to our analysis here, the IBGP, so-called internal BGP part here, which is 77 lines code. But still, it shows you how concise it is to program in Prolog for BGP systems. And more importantly, the meta interpreter, which is responsible of generating the explanation, is only 10 lines of code. In the repository, you will also find test generation code, which we used for the data plane explanation, which didn't appear here in the talk due to limited time, but we did briefly discuss in the extended abstract. We also have some utility code, such as pretty printing for the explanation. And in the next few slides, let me give you a little bit more feeling of how the Prolog code looks like. First, let me show you fragments of our BGP Prolog encoding. At the top level, to run the BGP system, we first initialize the network, initialize S, and then evoke the net procedure, which will run BGP in n steps. We explicitly run it in n steps because we don't know whether the BGP system will converge or not. And in each iteration, the net procedure will call a delta function that transforms the network state from S to its next state M. A network state is really just a list of 3 elements: routing tables, message queues, and pending nodes. And in each transformation of delta, we first pick a node, random pick a node out of the pending nodes for BGP process, which is the BGP process procedure. In the pick procedure, we make use of the member function. And that's the important part, because member function is what actually introduces non-determinism into our BGP code. In the BGP process procedure, as we can see here again, the Prolog imperative reading helps a lot. We see that BGP process is really just sequentially evoking these procedures. Compute a new route, locate where it is, inserting a new route into the queue, process a new route with BGP select route, etc. And BGP select route is a part where we actually do path selection, as we've seen earlier in the RFC example. In our simplified version of BGP, we only compare MED attribute and the next hop. So this should give you a high-level feeling of our BGP encoding, and in the GitHub repository you will see everything. And here is our meta interpreter. And you can see that our meta interpreter is really just a direct extension of the famous 3-line vanilla Prolog meta interpreter. Our meta interpreter is different from the vanilla version in 2 aspects. First, in addition to interpreting a goal, we also generate the corresponding proof of tree. Second, this proof of tree only collects relevant information. We selectively printing what's needed for explaining oscillation. In particular, we are only interested in collecting net. At a high level, each iteration net procedure, and the pick procedure, which node was actually being picked for BGP execution, and finally, the BGP select route procedure. For the rest of the procedures, we just hide them, don't print anything. And this is the meta interpreter. Running this meta interpreter on the wrong iBGP procedure we've seen earlier that describes the BGP system, collecting the proof of tree, selecting proof of tree T, and print it gives us a trace, gives us a selective trace that actually explains the oscillation behavior. So recall that in the beginning of this talk, I mentioned the significant advancement of network diagnosis from a black art with pin and trace route to formal analysis. And our effort here, obviously, is part of that big transition. But among all these efforts, I want to mention a specific tool called Badfish. Because Badfish is also based on logic programming. Badfish is a network configuration tool, uses Daylog as its evaluation engine. Originally introduced into the networking community 10 years ago. Ever since, Badfish has been the backend engine for many analysis tools used in both academia and industry. And in 2023, the Badfish team published an experience paper on the evolution of Badfish with very interesting findings. On one hand, they praise Daylog as a very useful tool to rapidly prototyping new analysis functions. But on the other hand, they also reported the limited expressiveness of data log and the lacking of performance, which eventually led them to abandon data log and how they moved away from data log to Java. In our research, on the other hand, while we agree with Badfish in the use of logic programming as a rapid prototyping tool, we argue that it's too early to abandon logic programming and stop with data log. In fact, in this talk, we made the case that Prolog is a very expressive tool for capturing complex, dynamic, non-convergent behavior of computer networks. And more importantly, Prolog can provide metaprogramming facilities that allow us to easily explain the non-convergent behavior of network systems. To conclude, we draw a parallel between formal network diagnosis and program analysis. Our main insight is that the majority of existing network diagnosis in clean-slate data center resembles program analysis in compilation, where the problems are oftentimes well understood, prefixed, where the concern is focused on performance. And as a result, solutions there will highly optimize the heuristics over carefully crafted representations. On the other hand, the majority of the networks where formal network diagnosis are needed more resemble programming environment. Here, the problems we are facing are more diverse. We need to support the entire life cycle of the system. And in addition to performance, usability also matters. And our main conjecture is that the tools developed for net programming environment, such as profiling, monitoring, tracing, and more sophisticated tools, including algorithmic debugging, programming, slicing, etc., have great potential in networking as well. And in this talk, we presented some very early stage, but hopefully promising result on using Prolog to implement an explanation generator. Moving forward, we will use Prolog meta interpreter as the injection point to include more new solutions, such as sophisticated algorithmic debugging and program slicing. So that's all my talk. Thank you, and I'm now ready for Q&A.
Okay, can you hear us?
Yeah,
Yes.
I can hear you.
Okay.
Sure.
Do you want to?
I have a question. Towards the beginning of the presentation, you mentioned the problem of oscillation. Is that one of the reasons why it appears? Is it because the policies are not prioritized? There's no ordering of those policies? I'm not very familiar with the domain.
Oh yeah, so I can quickly clarify. In the BGP system, in general, there are two sources for oscillation. One is what you mentioned on the global internet, the autonomous system, the so-called independent operating networks, they are not coordinating. There is no universally agreed upon guideline or policy. So the policy themselves can conflict with each other. Yeah, so this is the first type of oscillation. And there is also another source, the kind of oscillation that we were actually trying to catch in this extended abstract, which is due to partial visibility. So in this case, or in the example presented in the top here, you will see that the so-called MED attribute, it was only compared for a particular neighbor AS due to its semantics. So the comparison process, it doesn't compare all the candidate routes, it compares among the subset. But as you can see with reflection now introduced into the system, the reflector will selectively announce, reflect a partial set of points. So the combination of reflection and these MED semantics combined, they will create this very interesting partial visibility into the set of paths that, depending on what path you see, you will pick different best paths, and that can lead to oscillation. Actually, it has a close connection with monotonicity.
Thank you. Other questions? Okay, so let's thank the speaker again.